today's session.
Yes,
in
sir.
today's session, I'll cover circularly polarized metamaterial antennas. Correct. So this is one of the area where we are working at IIT Dhanbad. Correct. So before the CP metamaterial antennas, the idea was how to develop the compact antennas. Correct. So let me So let me introduce first about my institute where I'm doing all the research actually. So you can see this is a building actually where we are currently doing all the things. Correct. So we have all instruments, correct, and facility to do these research actually. Correct. And currently 7 PhD students working with me and 4 are already graduated, and my lab is actually sponsored from the DRDO, ISRO, CRB and other funding agency projects. So in today's presentation, I will try to cover these content. So we'll start from the motivation. We'll try to learn what are the electromagnetic metamaterial. Then we'll see the transmission line approach of the material. Correct? And most important, I'll discuss the CRLH transmission line, which is composite right-left-handed transmission line. Then we'll see the property of CRLH, that is ZOR, zeroth order resonance. Then we'll discuss about the fundamental limit of the antennas, and we'll see what is the circular polarization. Correct. And finally, I'll show you some of our findings, what we develop actually at IIT Dhanbad. Correct. So before doing anything, there must be some motivation, correct? And like the motivation, like if you can see this table, correct? A lot of application you can see different frequency, like starting from the GPS, WLAN, 2G, 3G, 4G, 5G, and ISM bands, correct? So now in a daily life, we are interacting with each frequency actually, correct? And now this is a part of our life, correct? So the second photograph you can see, this is a mobile phone, correct? Here particularly the blue font you can see where 6 antennas is marked actually. So you can see this is LTE antenna, horizontally polarized, LTE antenna, vertically polarized, Wi-Fi antenna, then we have a GPS, then PCS antenna and 2.45 gigahertz Bluetooth antenna, correct? So it means that within this small size, these things, we need to accommodate large number of antenna. So the thing is, one of the thing, what we want to do actually, if you see some of our work actually, we try to manage the multi-band antennas, correct? So like here you can see that these antennas are distributed over the area of the mobile, correct? Now, what we are doing currently, actually, we're trying to do over the same substrate, and we'll try to make it multi-band, correct? And keeping the fact that how we can do for the 5G antennas as well. So currently, we developed this thing is a cognitive radio systems, correct, which is a 5G antennas, correct, which comprises antenna as well as a multifunctional filter, correct. So that is actually one of the unique work. Correct. So let us discuss first that thing like what are the fundamental limits of the antennas, correct? So when we are talking about the compact antenna or miniaturized antenna, it is not like that we can go arbitrarily, correct? We can miniaturize as possible as it is not like that, correct? So antenna can't be arbitrarily small. This is one fact. Another is there is a trade-off between the size, bandwidth, and the frequency operation, correct? So the thing is, these three scientists, Wheeler, Chu, and McLean, studied theoretically that how far we can go, means how far the miniaturization could be possible. Correct. So this is one of the current one, McLean, which corrects actually the Chu and the Wheeler, and finally he given these theoretical formula by which you can see that what is the possible Q factor, radiation quality factor, and another is the fractional bandwidth, correct? So this is valid for the less than Q is less than 2, correct? and for electrically small antennas, which is Ka less than 1. Correct. So this is one of the important things. So those participants, those who are working in this area, correct, they validate actually these things. However, theoretically, you are getting sufficient number, and when you do the simulation, so the thing is, if the things are electrically small, you can verify. But I'll suggest you please go through and please try to verify. Okay. Now another thing is the before doing the things actually, correct. So we should see actually what are the main advantages we are getting with this microstrip sorry metamaterial antennas over the patch antenna, correct. So like here a very simple example I have taken actually. If you see, this is a patch antenna, correct, and normally these are the uh, formulas for calculating the width and length, correct. So what we did actually, we tried to manage it at 1.5 gigahertz. There is a purpose actually why I did actually, I will tell you. So at 1.5 gigahertz, we tried to find out its dimension. So what we found actually, we found that the overall antenna size is 100 by 100 square, correct. Whereas the patch size is 79 by 66.7 square, correct. This is a pretty large antenna at 1.5, and if you see the frequency, this is expected actually, correct. But we cannot deny this size, correct. Now the thing is like if you see this photograph, correct, we have taken from this paper, which is IEEE transition on antenna and propagation, published in 2011, correct, Jang and all. So you can see this picture actually. So what they did actually, they use the Mender line, they use the signal patch, and they use the coplanar structure. Okay. So here you can see the size of the antenna is 21 cross 25 square. Correct. Now this antenna is also working at 1.5 gigahertz. Now the thing is, you will see that the same thing, the same frequency could be accommodated in a small size. Correct. This is just 1 by 4. Correct. So this actually motivates us that can we make the compact antenna uh, for the smaller frequencies, correct, or rather I should say for the handheld devices, correct. So here you can see some of the comparison. So comparison, if you do the comparison, it will give you some negative things, correct. So those negative things actually we try to accommodate, and we try to achieve, we try to convert as a positive things, correct. So I'll show you in the coming slides. So if you see particularly here, so definitely we reduce the size, like here the 100 centimeter square, the overall size, and here the 5.44 centimeter drastically reduced. So if you try to calculate the percentage reduction, it is more than 90%, correct. Now on the other hand, if you see the gain and the radiation efficiency, means the numbers are horrible, correct. The gain is we are getting minus 2.15, and the radiation efficiency we are getting the 42.5%, correct. And I would say this is not going to be used for any kind of the applications, correct, because at least we require 1.5 to 2 dB gain to run this handheld applications, correct, and radiation efficiency must be above 75 to 80%, correct. So the idea is that how to improve these two parameters of the antennas, correct. So I'll try to show you that how we improved. Uh, but because I took a topic here, the circular polarization, so I'll focus over how we did the circular polarization with metamaterials, correct. So this is a research objective actually. So what we said for us that from metamaterial antennas, we can achieve the size, correct. And the second actually, which is the objective, we took actually this is exchange ratio bandwidth, correct. So when we started the antennas, also metamaterial antenna, the small antennas, correct. So that time, if you go the literature, so you will find mostly the linearly polarized antennas were published, correct, and the gain and the radiation efficiencies was it is difficult to accommodate for any kind of application, possible application. So when we started, we made actually compact antenna, and then after we improved the gain as well as the radiation energy. I'll show you some of our work actually later on. And then after we realized that CP antenna is okay, but the thing is because there is a problem of losing the signal and all the things. So CP is supposed to be incorporated in those compact antenna, which is one of the challenging tasks, correct? So we somehow manage, and last year we tried to develop an antenna. We published in actually IEEE magazine, and that is actually very good work. Correct? So I'll share with you that work, but how we manage all these things, correct? So I hope you went through all the historical review, because this workshop is mainly focused on the metamaterial. So let me quickly do these things, the historical review. So this is started in 1968, correct? Theoretically, and then after J.B. Pendry actually realized these things from wires and the SRR. Then after D.R. Smith actually experimentally validated, and these two guys actually done for the RF engineer. They try to propose the things from the transmission line concept, correct? CRLH and E2, correct? So what is the metamaterial? So metamaterial, like here, the normal material, you can say is an atom, correct? Electron, neutron, nucleus, and all the things, correct? So this is the concept actually, Jude module particularly. And when we are thinking about the permittivity and permeability, it is coming from the electric dipoles and the magnetic dipoles, correct? On the other hand, the metamaterial one, we are talking about this article. Correct, this is actually man-made material, and in a particular frequency band, these structures are showing the unusual properties. These unusual properties are actually what? This is negative mu and negative epsilon, correct? So mainly you will see the right-handed material and left-handed material, one of the terminology. Some people are also saying double negative material as well. So many terminologies are there actually, correct? One important point here, like for metamaterials, actually the K vector and the S vector in the same direction in a right-handed material, sorry, and in a left-handed material, this is opposite. Or we can say also the phase and group velocities are anti-parallel. So we can divide actually in 4 quad. This is the system is like the DPS, double positive material, epsilon negative, double negative, and mu negative material, correct? So these are some of the photographs of the common structures actually, correct, by which we can derive all those things. But our idea is as a antenna engineer, correct, what we are doing in a lab, correct, we are highly interested in the equivalent circuit, and we try to satisfy the CRLH property, correct, and finally we are utilizing it in the antennas, correct. So this is I must pointed out these things, that there are two approaches actually parallelly going on in a microwave engineering. One is resonant type approach, correct? Mainly we are also using this approach in developing the filters, correct, as well as the absorbers, correct. So basically the Smith given initially these ideas that splitting resonator and the wires could be the potential these things providing the negative mu and negative epsilon, while having this E should be parallel to the wires, correct, and magnetic field should be the normal to the y-axis, correct. So we are getting actually these negative mu and negative epsilon properties, correct. So after that, means if you see in the literature, actually you will find number of papers, and they try to arrange those structure, 3D structure on the planar structure, correct, and you can see the splitting resonator, and they also proposed complementary splitting resonator. You can see that these are the equivalent circuits actually. From this paper actually you can find the more details, correct. So mainly the thing is on the planar substrate they try to manage all these things, correct. And later on when you combining the structure, like here you can see one example where this is two patches are there, in between a gap is there, and beneath of that we have the splitting resonator, complementary splitting resonator. So the equivalent circuit would look like this, correct. Okay. So finally, in a with the planar technology, the people experimented with the SRR and the wire like this, correct, and they found that the things are still working with the planar structure as well. So then the things are started and the many application was boomed, like in a filter, these things absorber, antennas and all. Correct. And right now the metal surfaces and all these things are going on. Correct. So these are the some of the structure actually, and we should have the basic idea. Like the thing is, like if you check the many papers, the very complicated structures are there. But I would say that you please start with the basic structure, what the theory has been developed. Correct. So this is one of the paper actually I put it here. You can download this paper and you can find that some of the basic structure and its equivalent, like here, this is the split kind of the split resonator, and this is the equivalent circuit, and this is the dual of this structure. The equivalent circuit is here. So based on that, what kind of matching you want, correct, and what kind of dominance, like sorry, uh, inductor or capacitive actually coupling we want, correct. So you can manage with this, correct. So it requires the basic idea, correct. Now let us start with the transmission line approach of the metamaterial, correct. So this is, you can see, a very initial one. The CRLH approach was proved with these structures, correct. So before starting the CRLH, I would like to discuss some of the things of the transmission line. So here you can see in a transmission line, like in a shunt you have a capacitance, and in a series you have what, inductor, correct. So the thing is, like broadly if you see, so in a shunt we have the inductor, correct. Now if you go from the basic transmission line and you try to derive its beta, it is coming like this, it is negative, correct. So negative slope, correct. So if the beta is negative, so you can say that phase velocity and group velocity are anti-parallel, correct. So this is one thing, correct. Now the thing is, like with this structure, like what I have shown you, that initially the things were started with the interdigital capacitor at the stub, correct, and the V actually, correct. So here you can see this is a very old structure, correct. This is not a new structure, and the stub, correct. We have seen in a textbook also, correct. So what they did actually, Kalos, correct, and Ito, they try to is arranged in such a way, like interdigital and the shunt inductor, correct, and they connected with a VR to the ground, correct. So if you try to draw its equivalent circuit, so what will happen, definitely these fingers, correct, in gap will provide you the capacitance, correct, and this stub, and which is the V actually, which is going to connect with the ground, will provide you the inductor, correct. So mainly if you see, uh, the circuit is like the CL in a series and the inductor in a shunt, correct. But the thing is, as we know, on a microwave frequency, correct, we cannot neglect the other effects. Like if gap providing the capacitance at the same time, because due to the surface current there must be some inductance, correct, and you cannot neglect that inductor. And when you are dealing with a planar line, correct, so upper part, okay, and the bottom part will provide you some capacitance, that is correct. So we can, so ultimately the overall circuit, we can say, is comprises all these four elements, where L stand for the left-handed and the R for the right-handed, correct. And if you plot this dispersion diagram, it looks like this. Like for here you can see the omega SC and omega SH, omega shunt and series, correct. If these things are equal, so we are saying as this is a balanced line. Otherwise, these two frequencies will be there. And basically, the thing is how you are going to terminate your transmission line, correct. So mainly you are getting the shunt resonance and the series resonance. I'll tell you these things, correct. So this is what the implementation of the transmission line, correct. So if you put all the unit cells side by side, correct. So you can manage the transmission line, okay, that CRLH transmission line, correct. So these are the different dispersion diagram. I think we went through all these things, correct. So I'll not repeat. So this is what actually we are following actually in a lab, that how we can do. So we are extracting the parameters of the structure actually, correct. We are plotting the Gauss diagram and dispersion diagram, optimizing the things, correct, and all sort of things we are doing uh, to manage the CRS transmission line, correct. Now the thing is, in all of our work actually, we have verified all kind of resonators what we used actually in antennas by the circuit approaches. Correct? It is not a very actually difficult thing. Like you can also do like here, you can see in a dotted box. Correct? Two boxes are there. Correct? So one box representing the interdistrict capacity on the stub inductor. Correct? So for interdistrict capacitor, this is very known circuit, and for the step they manage like this. Correct? Now once you have these C and L, correct, you can convert in the impedance and impedance. So finally, what you can make a relation. Once you have the relation, so overall you can find what are the LR, CR, CL, and L. Correct. So theoretically, you will be having a guess that what type of means capacitance and inductor and how the things are dominating. You can predict. Correct. Now, so how you will extract? Correct. So the extraction is like that. You have a unit cell and you need to make a TM building. Correct. And you're supposed to use this formula to find it out. Its S parameter, and finally you can plot the dispersion diagram. Correct. So this is all in the part. I will not go into detail. I hope these things will be covered from the previous speaker. Correct. So these are the some design parameters and all. Correct. Okay. Now let us understand these things. You know, zeroth order resonance. Correct. So as I shown you the dispersion diagram, correct. So it allows actually what that the resonance index, which is M here actually, symmetrically we can define around its n is equal to 0. Correct. So we have a provision here, negative side and the positive side. Correct. Now the thing is like if you try to plot the voltage versus electrical length, correct. So what you will find here that different resonance index, correct, m is equal to 0, plus minus 1, plus minus 2, plus minus. Why this is coming? Because if you have the number of unit cell is n, so total number of resonance point will be 2n minus 1. Okay, so this is the funda actually. That is why they put it like this, correct? Now, so for particularly if you see m is equal to 0, there is a straight line, then m is equal to 1. Okay, lambda by 2 like that. Lambda 3 lambda by 2 like that, correct. So the thing is like if you if you observe from this graph actually, particularly m is equal to 0, this is the magic is happening actually. And what is that you are getting a constant voltage, correct, or we can say the equipotential surface, correct, over the planar transmission line, correct. Now, so this is somewhat actually will provide you some idea actually that because at beta is equal to 0, correct, you can manage any number, correct, of the frequency, because you can accommodate the higher frequency, you can accommodate the lower frequencies, correct, by tuning your left-handed inductance and the capacitance, correct. So this is what actually one of the very important outcome of the CRLH transmission line, that this is independent of the physical length, correct. It means that the idea of the miniaturization is coming from here, correct. Now we have the two different terminations here. That one we terminated with the open, terminated as open-ended. Okay, so in that case we have only the shunt elements. So the shunt element will be deciding your the resonance, correct. That is why these 2 points you can see, correct. And when you terminate with the short-ended, so the series element will be provided you the operating frequencies, correct. There is a one more validation I would say, correct. You can do in lab, correct. At m is equal to 0, beta will be 0, correct. Lambda is infinity, so the fields will be vertical, correct. These are the first order resonance actually. So you can see some fields are up direction, some fields are down direction, correct. Now let us understand the infinity wavelength of the antennas with monopole radiation, correct. So mainly if you see the ZOR, it will provide you only directional radiation pattern. The idea is quite clear that if you compare with the patch antenna, only two sides are contributing in a far field. On the other hand, if you see the CRLH antenna, all sides are contributing. It means a circulating magnetic surface current actually, and you are getting the radiation pattern like this, correct. Okay. So later on, people are also tried with the wireless geometries, correct. I'll not go into details this thing. And there is one slide actually very important. We try to compare these two things. So we develop a patch antenna and versus the CRLH antenna at 2.4 gigahertz. So we design the things, and these numbers will which I'll try to show the numbers here. So for the patch antenna and the CRLH antenna at 2.4 gigahertz, particularly, you can see the patch cell size is 45 cross 29 mm square, whereas the CRLH antenna is 21 by 22. Correct. So the gain is definitely a less, but it could be utilized for some applications. Correct. And here, if you can see the sum of the characteristic, correct. So we manage almost same bandwidth. Correct. Gain is quite less. Correct. And the thing is, we have the radiation which is comparable. Correct. So the thing is, what we did actually here, we just manage some metallic post here. So it is going to radiate in a particular direction. So it is actually a directional antenna, like a patch antenna. In a particular broadside direction, it is radiating. Correct. So the thing is, like we are converting its omnidirection to these things by holding the post. Correct. So in this way, the gain is improved actually, and now we can say this is comparable to the patch antenna. Correct. So like if you can classify the antenna, so we can classify like this, that purely the CRS transmission by transmission line based antenna. Then we have the loading, correct, and we have the meta-resonancy and the meta-resonances, correct. So now, like here, if you see completely, we are following the CRLH approach, correct. Later on, if you want the number of bands, correct, if you want to improve a particular band, correct, so you are loading with some metamaterial cells actually, and later on, the idea extended to the meta surfaces as well, and now we are using for the gain enhancement and the beam steering as well, correct. So let us try to understand the circular polarization, correct? Why this is important, correct? So first, we should know what are the conditions that it has two orthogonal components, correct, and the magnitude should be same, and it should have the time phase difference of all multiples, which is 90 degrees, correct? So this is actually the condition actually is supposed to manage in the structure, correct? Okay. And what it provide actually, it will provide the higher link reliability, correct, and immunity from the Faraday's effect, atmospheric condition, and all the things. And finally, here I would say that polarization losses is you can neglect actually, you can minimize phasing issues, correct, mitigation of the multi-part propagation. Correct. Here you can see one of the picture actually. So when your incident wave and the antenna polarization is same, so you are getting the PLF1. Otherwise, it depends upon the cos phi this term actually. Correct. So if it is orthogonal, you are not getting anything. So the thing is, like if you have the horizontal polarized and the vertical polarized, or in your mobile, like what you are using the LD mobile, it having the two actually polarized and two polarized antennas, like vertical polarized and the horizontal polarized. So many times we are not using the information, and particularly MIMO we are using. So it provides you the extra diversity, and we are getting the signal properly, correct. But the thing is, if you improve with the CP property, correct. So the thing is, the chances, the diversity, and all the things, and the polarization losses will improve, correct. Now, some of our finding I would like to discuss with you, correct. So this is one work actually done by one of my MTech students, Samir Kumar Sharma, correct. So he published in IEEE transaction. So this is our work, or you can say this is the first work actually, correct, based on the ENG transmission line, correct. So later on, what we have seen that CRLH is okay, because the thing is, some higher order modes are also coming, and sometimes our focus actually on the higher order mode, correct, and we are deviating from the ZOR mode. So here what we did, we propose actually ENG line, correct, epsilon negative. What we did for this epsilon negative, we just removed the CL part. Okay, what is that CL? That left-handed capacitance, correct. How you can remove that? Providing those slots or gap actually, correct. So that those interdigital fingers you have seen, correct. So those fingers actually we are removed. I'll show you this thing. So this is the geometry actually, correct. Here you can see. So what is the contribution? The contribution is actually, this is like you can see, this is a very small antenna, correct, and it follows the ENG approach, correct. And here you see the bow type shaped patch, correct, which connects to the signal patch. This is the feed actually, and this is the upper ground, correct. Now what we did actually, we did an extra thing. like we provide a reflector, correct, at the back side of the bow tie shaped patch, correct. You can see this A and A, this is this metallic patch actually backside of this, correct. So what happens actually when we arrange in a such a way, correct, so drastically the frequency we accommodated a very small frequency, correct. I'll show you. So the thing is, like if you see particularly this graph, correct, so you can see that particularly this red dotted curve, correct, is for the first structure when we don't have the lower ground plane, correct. And as soon as we incorporated the ground plane, it reduces to 2.4 gigahertz, correct. So it is 1.3 gigahertz shift. The reason is quite clear, correct. The reason is what? That we introduce extra capacitance due to the ground plane, and because of this bow tie and the ground also providing some capacitance. So we model it and we try to find it out the formula, and we verified that yes, it is working, that due to this capacitance, actually extra capacitance, correct, generated actually, correct, in a shunt arm, correct, we manage this lower frequency. So the what is the magic is that in a simple in a same design, correct, we accommodated the small frequency as well, correct. So what I would say here, that the miniaturization level is 57.9%. This is quite a big number, correct. And here the K is less than 1, so still it obeys the miniaturization or electrically small antenna, correct. We can say electrically small antenna. So this is what the measured result actually what we found, and it follows the omnidirectional radiation pattern. The idea is same. The circulating magnetic surface current is around the antennas, and we are getting these things, correct. Now the problem was the gain was very less actually. So what we did actually, we used the electromagnetic band gap structure, correct, and we try to reduce it, correct. So when we reduce the capacitance, actually it enhances the bandwidth, and at the same time we got a loss. What loss? The frequency again shifts to the higher side, but not a very higher side like what I have shown in a previous slide, correct. So still we are managing a small, accommodating a small frequencies within a small size, correct. So you can see this is EPG structure we manage over the upper ground plane, correct. So you can see here, this is a very good actually picture. So here you can see the first is what, without backed ground plane. Then we have backed with a normal metallic plate. So we are working at 2.4, and as soon as we accommodate the EPG structure here, so it will start working at around 3 point this thing 3.2 or 3.4, correct. But here the bandwidth is increased. The reason is quite clear actually. If you try to derive the formula from this thing, so you will find the capacitance are responsible, because due to this gap actually, sorry, due to this gaps actually, the distance, the extra capacitance over the surface, the series, correct, and overall capacitance in the shunt actually decreases, correct. So finally I would say that we got average peak gain is 2 dB, and the radiation efficiency is 91.3, correct. So we in a very small antenna, correct, in a very small antenna we try to achieve all those things, correct. Now later on we start working over these things, and we developed another small antennas, correct. And in this time what we did, this was not going with the conventional design, correct. And the same idea, we utilize the background plane. So over the same plane, correct, we did not accommodate the ground plane, and we backed actually the radiators. So you can see here, this is geometry, and this is the formula we derived actually, correct. And particularly two resonance we got, one is a ZOR, another is lambda by 4, correct. So this is one of the approach. The idea is that we try to back uh, the antenna actually with this metallic patch, correct. And this is actually, I would say that in a small antenna, this is done by our group actually, and we propose this thing for the possible miniaturization, correct. Here, these are the some of the validation. As I told you, we can validate this ZOR by plotting the vertical field. So we can also do the things, correct. And other surface current could be utilized to find it out that this validation is correct or not. Like here, one thing you can see here from this graph is very interesting actually. That particularly this connecting to the radial stub actually. So this length is LM1. So when you are changing actually, correct, when you are changing, so only the ZOR part is changing, correct, and the first resonance is not changing. This is one of the validation. By varying the parameter you can also validate the structure, but I would say that you can plot the vertical field and you can, correct, these are the major results, correct. I'm not doing. Now the thing is, this is what actually what I want to discuss with you. So now we have the enough background to understand this CP metamaterial antenna. Now what I have shown you, quickly I will summarize with you that we have seen the CRLH approach, correct, and we have seen the ZO, how the ZO are working with this CRLH structures, correct, how we can do the miniaturization, correct, and what are the techniques actually we use, like ENG, one of the possible way to reduce down the size as well as the background plane we used actually, correct. So these are the techniques actually we utilize in the past. So 2018 onwards, we took a challenge that how we can incorporate the CP in the small antennas, which is made of the CRLH approach, correct, and we succeed actually, correct. That how the things are working. So it requires some basic idea that what are the field components, how you can manage the electric and magnetic field. The one thing is clear, that from the ENG structures, the fields are vertical over the surface, correct. Now the thing is, another, like if we can manage the horizontal fields, the electric field in a plane actually, so the orthogonal field could be managed. Now the other part is that how we can manage this 90-degree phase. So for managing this 90-degree phase, you need to little bit do the optimization, right? Because the thing is, when you are combining the two structures, correct, and operating almost the same frequencies, correct, and providing the different polarization, correct, and if you want to manage a phase actually, correct, so what you need to do, you need to do some changes in this electrical length, and hence you can say that you are altering actually the phase, correct. So I'll show you. Okay, so this is one of the very simple structure. We don't want to complicate it, correct. And the thing is, if you see this structure, you will say, hey, what is the metamaterial actually, and what means what is the idea. So this is just made of very simple things, correct. What proposed in late 90s actually, those structures. So here the structures are the rectangular stuff which was used as a virtual ground plane, correct. Another is a circular ring which provides with the inductance, correct. And this is the right-handed inductance that we provide, and this is a feed line, correct. And this thin strip line which connects you, which connected these things to the virtual ground will provide with the left-handed inductance, which is LL in shunt, correct. And what we did, we loaded with the single split ring resonator, correct, at the back, correct. And this is the partial, correct. So the thing is, what experience we have, we accommodate all things here. The first was the ENG transmission. So here you can see there is no capacitance, there is no scope of capacitance here, correct. Dominating capacitance, correct. Definitely there would be a capacitance, but dominating capacitance is not there, correct. So CLV completely neglected. So definitely I'll say this is the ENG transmission. The second part, that's the partial ground plane. Many of you are using the partial ground plane. The reason is quite clear that we want a sufficient bandwidth, correct, to manage the capacity. But once you reduce this bandwidth and all, this capacitance and all, so you are losing the antenna performance level. So we need to accommodate. That is why what we did actually, we provided a virtual ground plane, extra virtual ground, correct. So please take care of this part also. This is also a ground plane which provides a very high capacitance, correct. Okay, but it is not responsible for the radiation, correct. Now the thing is, like these are the parameters I put it over here, correct, and the size is actually here 0.26 by 0.16 lambda naught square at 3.5 gigahertz. Mainly this is we designed for sub-6 gigahertz, correct. Now if you see the design stages, correct, so I'll try to explain that how the CPU is coming in, correct. And this is what actually interesting, and this is what the idea is actually what I want to discuss with you. Okay, so this is the top view actually, correct. And like we named actually antenna 1 and 2 and 3, like the audience can understand the things. So we started with the feed actually, and then we attached this ring and the virtual ground plane, and then after at the last we loaded at the back with the single split ring, correct. Now the thing is, if you see the antenna number 2, correct, which is without bagged single split resonator, we have only one, correct. As soon as you accommodated a single split resonator, correct, the second resonance point is also appearing, correct. The reason is quite clear, correct. I'll show you that thing, this equivalent circuit and all, correct, and you can find this resonance point, correct. So when we are merging these two, correct, we taken the size such as that these things should be must be closer to each other, correct. So we got a very nice bandwidth as well, correct. And as soon as we got the actual issue bandwidth as well, correct. Now you will the question is how, correct. What the things are happening, those who are working in the planar antenna and particularly CP antenna, they must have seen the cross slot, correct. And what is the idea of the cross slot? The idea is that if you see the electric field, it is orthogonal to each other, correct. And by varying the width and length, we are managing actually what its phase difference, correct. So that completely you can say this is a circular polarized, correct. Now, so finally, the thing is one exercise we are doing in all the antennas, that it's equivalent circuit, because we are following the CRLH approach, correct. So it is really valid that we supposed to do its equivalent and find it out all the possible capacity inductance, correct, so that it could be further verified from the circuit approach too, correct. So here you can see these things, that different inductance and capacitance we manage. The idea is quite same, correct. Here what I've shown in CRLH line, correct. So here you can see the L1, correct. This is due to the field. Then L1 and LR actually due to this field and this things, this ring actually. And then after we have a shunt element. So shunt element means what? We connected with the virtual ground plane with LL. So this is the LL actually, correct. This is the LL. And here you can see due to this partial ground plane, we have a capacitance as well, correct. And this is the capacitance between what? The radiating element as well as what? This ring, okay, and this partial ground, correct. And finally we have a capacitance too, correct. So now this is what for the upper part, correct. Okay. Now how we will accommodate the equivalent circuit of this backside single split resonator, correct. So the thing is, this has already been done by these peoples actually, and they publish in IEEE transition on microstrip technique. So we took straight away, correct, this single split resonator and its equivalent, what they given in paper, and we just added, correct. And we found that this is one of the validation of these things also, that yes, what the things are published, we're supposed to validate too, correct. So this is exactly the things are working with here also. So this is the complete circuit diagram, I would say, and what we did actually, we put it in areas and we cross-verified all the things, correct. And the thing is, if you try to find it out as ZOR, so the expression would be like this, correct. And for the frequency for circular split resonator, this is the expression. This expression we taken from this paper, correct. Then after the thing is one thing actually I missed, correct. Sorry. So before that, before jumping over all the result actually, I would like to clear how we are getting the CP actually, correct. So the thing is, this is ENG transmission line. Like if you plot the electric field will be normal of these things, correct. This is quite clear. Even if you go with the simple microstrip approach also, so you will find the many of the electric field are normal to the surface, correct. Now, at the same time, when you incorporated this single split resonator, correct, what you will see is a gap between, correct, and this will provide you space here to accommodate the planar electric field or horizontal electric field. So the thing is, you have two orthogonal field components. Now, after that, how we accommodated its phase actually 90 degree, we try to enhance the radius of this single split resonator, and hence changing the electrical length. Definitely, there will be phase change, and at particular these things we got a 90 degree phase shift between these two components, and hence we said actually that we got a CP condition, correct, and this is validated, correct. Now here if you see these are some of the validation, we done actually LS is actually LL, correct, and this is open-ended structure actually. So that is why changing the LS actually this ZOR frequency is changing, correct. Okay, and particularly if you change the width of this thing CS, correct, there is a no change. Okay, so this is the beauty actually of this CRLH transmission line, that when you have the open structure, correct, so only the shunt parameter will be responsible for changing the resonance, other will not change, correct. This is one of the things, correct. So theoretical proof also, I would say. And further we validated with the equivalent circuit and all. What we found that dispersion diagram and other things are quite clear actually, correct. Now here you can see one of the proof also for this these antennas. So particularly if you try to plot the surface current, correct. So ZOR is mainly due to this shunt elements, okay, and the shunt elements coming from this very thin line, correct. And if you plot at 3.7 gigahertz, correct, okay. So if you see the back view, so single split regulator is only responsible for all sort of things, correct. So we can say that these two resonances are actually individually, you can control the upper geometry, okay, antenna geometry, and the this loading element, correct. Now this is one of the proof actually what I told you this earlier actually, that by changing the radius, correct, of this bagged single spectrum resonator, correct, you can manage the phase shift between the two orthogonal components. And this is quite clear. When you are changing actually, you can see the axial ratio is drastically changing, correct. Like the thing is, just having the orthogonal component will not serve the purpose of the circular polarization. It requires the 90-degree phase shift too, correct. So this changing the electrical length at some optimum radius actually will provide you a axial ratio bandwidth, and this is what actually the acceptable to. And now if you try to plot the bulk electric surface current, so you will see at a different angle it is start rotating, correct. So this is one of another validation. So we try to prove actually that how the things are happening, why the things are happening, and how we can validate these things also, correct. Now finally we performed the experiment, and we got very good results actually. We got a very good agreement also too actually, and between 3.32 to 3.90, we got around 15.44 percent bandwidth, and axial ratio is same also, is around 7.25%. This is quite good axial ratio and could be used many applications, correct. Like many of the space applications too, correct. And then after we have seen the gain also, and what we found that okay, let's say radiation we will say is quite acceptable, because the backed splitting resonator is there, so improvement is there actually. And the gain, if you see, this is roaming around 3.2 distance around 2, correct. So the thing is, like, we want a very good gain actually, because some of the space application we require a gain at least 3D, correct, more than distance, correct. So, if I summarize here, so the frequency what we have actually 3.5, we got the bandwidth 550 megahertz, axial ratio bandwidth is 7.25, correct, and the gain is 2.7. The efficiency is quite less, so we'll try to improve, correct. Now how we improve later on, the thing is, what we did actually, we used meta surfaces, correct. Like here we used artificial magnetic conductors, correct. The idea is quite clear, correct, and a lot of things already happened, correct. We just integrated here. So like if you see the PEC, correct, and if the wave impinges over the PEC, so definitely 180 degree phase shift we are getting. Now what is the property of AMC? We are not having the phase shift in a reflected wave, correct. This is one of the property. Otherwise what will happen, if you you can manage a high gain or improve the radiation if you back with a metallic plate, but you're supposed to put at lambda by 4, correct. This is one of the restriction, correct. But using the AMC, this limitation you can manage it, correct. So in this way the compactness and the whole volume could be small actually. You can say the the volume will be small, because this is going to be a 3D antenna, because when we are backing it, so this is not a planar antenna actually, correct? Okay, so this provides actually 0 degree phase shift. This is one of the things that improves the front to back ratio, correct? That is why we design an artificial magnetic conductor, correct? So this is the analysis we performed actually, correct? And we took this structure, correct? We made an array of this structure, correct? There is a logic actually what array we should take. I'll show you some of the simulation, how we selected those things. So we done an analysis, and what we found, we tried to manage such a way its capacitance and inductors, correct? We cross verified with the ADS also, correct? And what we tried to manage it at the same frequencies, that where this antenna is working, correct? We designed this AMC where the same antenna is working, correct? So here you can see, here you can see, this is working at the same. Okay, this shaded area 3.3 to 3.99 gigahertz, correct? 690 megahertz. Now we integrated. We also seen some of the different phases, and we found that is okay, correct? In between that, correct? The phase shift is the gradual change we are getting. So this is quite acceptable, and we can use as a AMC reflector, correct, in our antenna, correct? So finally, here you can see the miniaturization is we got 38.7, because this is structure actually we took from one paper. This is a complementary of that structure, correct? Further, we tried to validate its circuit parameter and all things, because we know there is a well-established story for AMC, correct? So this is actually what, this is a LC resonator, you can say, correct? And this LC resonator cavity kind of things is backing your antenna, correct? So finally, we did some of the parametric, and we found that what actually happened. So what we found actually, the changing of the height actually, so somewhat this would be more sharp, correct? So we took actually 3.2, correct, this value actually, correct? And we used actually this value to design our antenna, fabricate our antennas as well, correct? And later on, one more analysis we performed actually here, which is different arrays actually, means like 3 cross 3, 4 cross 4, like that, correct? It is not like that we can, it means you are free to use 10 by 10, but the thing is the concept of the miniaturization will goes on, correct? So it means that we sufficiently find a ground plane, correct, or a reflector, so that we can get a acceptable gain and all the things, correct? So we run the simulation, of what we found that these things, that 5 cross 5 will provide not deteriorating your acceleration, as well as the input impedance bandwidth, as well as the gain also, correct? So this 5 cross 5 we used actually, correct, and this is a sufficiently large these things, correct, to back this antenna, correct? And further we run some simulation over these things, different heights and this, and what we found actually, this heights actually somewhat changing the input, not actually matching, somewhat it disturbs, but overall the bandwidth is remains same, correct? And one of the things actually, it affects your axial ratio. What we observed, that this affects your axial ratio. The reason is actually quite clear, because we are backing with this AMC, correct? And the thing is, because when the reflected wave is coming, correct, so it disturbs your what the phase actually, what happening between your single spectrum resonator and antenna, correct? So you need to take care, you need to verify, correct, these things, correct? So you can take a run actually over the H2, and with the height of the distance between the antennas and your AMC, correct? So this is the thing, correct? Now, so finally, you can see this is a geometry we place like this, correct? This is a form actually we use to separate the things. Okay, so here you can see we improved the things. Now you can see we did not disturb the operating band, correct? It is still same, correct? So you can see this is without MS, and with MS, and without this things MS. All the things are there, and we are not disturbing the band, correct? And as well as the axial ratio bandwidth is quite it's okay in this band actually, acceptable, and you will see that you will surprise that we improve the gain and radiation efficiency. And this is very good actually. Correct. Here, if you see that with AMC structure, we have 80% efficiency and the peak efficiency is 88.4. Whereas for without, you are getting 72 and 82. Right? So it's good number actually. We increase by 10. Correct. And if you check the gain actually, correct. So gain with AMC, you have a very good gain. It's around 5 or between 4.8 to 5 dB. Correct. It's quite good gain. Correct. So now I can say that what I accommodated with this single antenna, that one thing is circular polarization I maintained. Correct. Another thing, I improved the gain as well. Correct. And keeping the fact that CRLH is still there actually, that particular theory is still valid here. Correct. So we did all those things. Correct. Now this is the radiation pattern, and radiation pattern must be in a direction. Correct. Okay, this is not this is a very obvious actually. Correct. So particularly this was a structure actually. Correct. This is a paper where we took the idea, and what we did, we make a dual of this. Correct. And making the dual of that, you will see that the capacitance value actually we maintain the same. Correct. So this is similar kind of things, but you can say by making the dual of this, we can miniaturize the size of 38.7%. Correct. So this is one of the things. Now, one of the very important results I would like to share with you, that if you see the action ratio here, and what we did actually, we try to check the action ratio between plus minus 45 degrees. This is somewhat very difficult actually, and in most of the handled applications, correct, you require this plus minus 45 degree. Correct, because this beamwidth is sufficient to run almost all the applications. Correct. And we also check the gain between plus minus 45 degree within this band, and we found this is greater than 3.34. Correct. And this is suitable with this handled applications. Correct. Straight away we can use. Correct. So the thing is, this is a complete package, I would say. Correct. And this plus minus 45 degree, I would suggest to the audience, you please check the antenna, because sometimes we are making the antennas correct, and we are getting the peak gain or this things, and we are saying that this is the antenna. Not actually, like you have to check whether the sufficient beamwidth you are getting or not, correct, sufficient gain is getting or not, or what is the this compactness. Correct. So nowadays, because this is the era where we want to keep the things our pocket, like your mobile. Correct. So we want a small distance. The antenna is one of the notorious item actually, I would say. Correct. So we need to handle it smartly. Correct. So in the same line, later on we did work actually, and here the approach was somewhat actually conventional, I would say, because here we used the two CRL structure and we placed orthogonal. Correct. You can see we placed the orthogonal and we backed again with the AMC. Correct, to improve the gain. Correct. So here this is the same idea actually. Correct, what we published in IEEE magazine actually last year. So the same idea, but the thing is here we are maintaining the orthogonal field component by having the two different CRLH structures. And the other question will be how you are managing these things, that the angle actually, the phase shift between these two orthogonal components. So I would say that there is a I'll show you these things. So if you see this picture actually, correct. So you will see this is P actually, correct. So this provides actually the changing of the electrical length of this P will sufficiently provide you the scope varying this phase shift, correct. And by changing this actually, we got a proper circular polarization within the structure, correct. So particularly for this structure, correct. For this structure, we done all sort of exercise, correct. And what we found, this is a proper CRL structure. This is not a ENG structure, correct. And this is validated with the circuit analysis also, correct. The same kind of analysis what I've shown actually, correct. And here if you see the size, this is quite small, and this is 0.088 lambda naught into 0.19 lambda naught at 2.5 gigahertz, correct. Bandwidth is quite acceptable, correct. So idea is same. We have the virtual ground, we have the shunt inductor, we have the series gap which provides the CL, correct, and we manage like this, correct. Okay. Now here you can see, while changing the P actually between this gap, you can manage your phase shift, and hence you can manage the axial ratio bandwidth as well. Correct? Okay. This is the equivalent socket. Correct? So the same approach we used here, and we try to find it out two different frequencies actually. Correct? And further, we design AMC meta surfaces actually. Correct? And what we found, we designed at the same band actually. Correct? And then we incorporated these things with the antenna. Correct? And this is the same analysis what we performed in the last things. Correct? So finally, the structure, if I show you, correct, the results actually. So the results like that, we are getting the bandwidth is 2.18 to 3.04 GHz. This is 32.95 with 60 megahertz. Correct. We have actually a bandwidth around 15.92. This is quite high. Correct. And we improved the gain, and this is about 3.5 dB. Correct. So same sort of things we manage, but here the approach of the circular polarized antenna is different. We place the thing orthogonally, whereas in a first structure, what I've shown you, I try to manage the different electric form from conventional structures. Correct. So these are the two approaches could be managed. But the thing is, before that, we validated whether this follows the CRLH approach or not. Correct. So these are some comparison, and recently in 2020 actually we published some of the structures actually. We keep working over the CP antenna, and we got very good bandwidth. The idea is almost same actually, correct? And we coupled with the different structures at the back, correct? And we loaded with some of the stuffs actually, so that the orthogonal field could be managed, correct? So we'll not go into detail, correct? So these are the some of the findings which we done actually recently, correct? So if anyone is interested, they can download and they can see, correct? So finally, I would like to acknowledge my students, correct, who worked actually very hard. And this is Mr. Mohammad Abu, who worked actually the CP antenna, CP metamaterial antennas, correct. These two students passed out, and they contributed in linearly polarized antenna, Mr. Samir Kumar Sharma and Ashish Gupta, correct. Thank you so much for listening. And if you have questions, I'm open for the question.